Greetings and welcome. In this video session, we will discuss about the numerical on HVAC cooling load. In previous video session of HVAC session, we have seen the theoretical treatment for the cooling load calculation for the case mixing before cooling coil. Objective of today's video session will be solving the numerical based on the case mixing before cooling coil. For getting the different parameters means sensibility factor parameters, cooling capacity and fresh air and recirculated air quantity. So for that, let us see first of all statement of the numerical given. Here is a given case for air conditioning hall. Following are the details. In the room, sensible and latent heat sources in kilowatt are given. Outside air condition and room side air condition is given in the form of dry bulb temperature and relative humidity. Apparatus dew point of cooling coil is given. Ventilation requirement for this numerical is on the basis of percentage of fresh air and recirculated air. So here 30% of fresh air and 70% of recirculated air is suggested. And we have to find the values for room sensibility factor, grand sensibility factor, effective room sensible heat factor. Then bypass factor of cooling coil, capacity of cooling coil and fresh air and recirculated air flow quantity in kg per second. So from the given data, condition of outside air and inside air, we plot the points for outdoor air 36 degrees Celsius dBT. Here is a 35, this is a 36. From 36 degrees Celsius dBT, we project in upward direction. And another parameter, that is a 60%. So on a 60% RH line, here we find the point, that is a point number O, outdoor condition. Similarly, for room side, 24 degrees Celsius dry bulb temperature, here is a 25, before that 24. So from the 24, we project in upward direction and relative humidity is 50%. So on a relative humidity line, 50% line, we find this point I, that is the indoor condition. We join OI. Then we draw a horizontal line through I and a vertical line through O. Thus we get this point intersection A. This is helpful in a further process to find outside air sensible heat and outside air latent heat. Now these 3 points we project on the enthalpy scale. This is an enthalpy scale. So thus we find the values of point O, I and A on the scale, which are shown here. Then we will enlist all these values here. So here we have enlisted the value from the chart. HO, HI and HA, we are using this value in a further procedure. After that, we have to locate the mixing point, which is between outdoor and indoor condition. So for that purpose, we will take the reference fresh air and return air percentage given. So here we have to locate this point 1 from point I at a distance. For that, we have to measure a distance between point O and I. So that we have measured, that comes 90 mm. So I1 is equal to 0.3 times. So here, if you, this is a fresh air percentage. This we can use on the opposite side, that already we have discussed in a theory part of this mixing before cooling coil concept. So as per that, I1 length is equal to 0.3 times, because fresh air is given 30%. 0.3 times of this total line length, that is a 90 mm. So this comes 27 mm. So we have to locate point 1 from point I at 27 mm on a line OI on the chart. So here this is a outdoor point, this is a indoor point, and from point I 27 mm at this distance if we locate, so here will be that point will come, that is point number 1, and this point line from this point if we project on the scale, that is a enthalpy scale, so that is coming H1 value 62 kilojoule per kg. 62 kilojoule per kg. So that enthalpy we will include in the calculation. H1 is equal to 62 kilojoule per kg. So this is a enthalpy of air entering to the cooling coil. Now we are given here ADP, that ADP point we will locate. That ADP is given 5 degrees Celsius. 5 degrees Celsius. So that point will be here at 5 degrees Celsius. On saturation curve, we locate the point ADP. Then we join this ADP and point number 1, that is a mixing point. Thus we get this is a one line. That line will help us to find the point number 2. So for that now we have to proceed for the room sensible heat factor calculation. Room sensible heat factor calculation, we use the given data RSH and RLH values in a kilowatt. RSHF is equal to formula RSH divided by room sensible heat and room lateral heat sum. So by putting these values, we find here room sensible heat factor as a 0.75. This value, room sensible heat factor value, we have to locate on this sensible heat factor scale on the chart. So here on this sensible heat factor scale, room sensible heat factor was 0.75. So this at 0.75 we have located, we say this point as a point B. Then we have to use a reference point that is called as alignment circle, that is at 26 degree Celsius DBT and 50% RH. So this is a 26 degree Celsius DBT and 50% RH. So this is a 50% RH line. So here we find this point. So this point we say as a point A. Then we draw a line joining these 2 points, means AB. We join AB, point A and point B. This line we get as a reference line. Now to this AB line we have to draw a line through point I, that is indoor condition, and this line we draw parallel up to the saturation line. So here we get the intersection of line 1 ADP, this line, and this parallel line drawn to this reference line AB. So here we get this reference point. So that reference point we say as a point number 2. So here this is a condition of air leaving the cooling coil, that is a point number 2. So this point if we project on the dry bulb scale, here we find the dBT of this air 12 degree Celsius. So condition of this air leaving the coil, that is coming 12 degree Celsius, and enthalpy, if you say, so for that purpose you have to project a line from point number 2 on enthalpy scale. So here you will find enthalpy of this point H2, so that comes 32. So in this way we can use now this value in a further calculation, and also this temperature also is usable in further calculation. In further calculation we go for dehumidified air quantity, so that is m dot d. For that we use the formula room total heat is equal to m dot d into hi minus h2. So from this point I and point 2, this is a load which is added by the air in the room to the air which is coming from the cooling coil. So that load is hi minus h2, and room total heat is what summation of RSH and RLH, which are given in the numerical. So by putting the values here, we find the value m dot d, that is total air passing over the cooling coil. Then as per the given percentage, we can calculate here supply air, that is a fresh air, which is a 30%. So that is like 0.3 times dehumidified air. So we find this value in kg per second. Similarly, return air or recirculated air is 70%. So that is like 0.7 times dehumidified air quantity. We find this value in kg per second. So thus we get the answers for supply and return air in kg per second. And this supply air means m dot o, means outside air, and recirculated air means m dot r. These notations we have used in our theory session. So these notations we will use for the further calculation. So in the calculation of GSHF, here we have to calculate OASH and OALH, means outside air sensibility and outside air latent heat. For that purpose, here this already we have done triangle formation, and we have obtained the value of I, A and O. So enthalpy of HO, HI and HA we will use in the calculation. Already we have discussed about it, that horizontal difference is HA minus HI, that is what sensible heat. So formula for OASH will be equal to what? M dot O. M dot O is the outside air, means fresh air. We have calculated it, multiplied by enthalpy difference, horizontal, by putting the value which we have received from the psychrometric chart. We put and we get the OASH in kilowatt. Same OALH, for that we take this vertical line difference, means HO minus HA difference. So putting the value from the psychrometric chart and m dot O value, calculation, we get this value OALH. Then grand total heat is what? RSH plus OASH, and another side RLH plus OALH. RSH, RLH are given in the numerical, OASH and OALH are calculated. So putting all these value here, we find the grand total heat in kilowatt. Then we go to the calculation of grand sensible heat factor. Grand sensible heat factor is equal to what? GSH means grand sensible heat, which is a sum of RSH plus OASH divided by total, that is a GTH, already we have calculated. So RSH is given in the numerical 300 and OASH we calculated previously. By putting this value and GTH here, we find the grand sensible heat factor that is a 0.534. Now this value we locate on the scale as a point C. Here on this scale at 0.534, here is a 0.5, here is a 0.55. So here 534 will come here. This point we locate, we give the name to this point as a C. Then we join alignment circle and this C point. That is a line AC. This AC line we get reference line. And now already we have joined point 1 and ADP. Now here this 1 dash ADP line, which is shown here, a red color line, this red color line, and this AC line, which is showing here grand sensibility factor. These both lines should be come in parallel. So in this way, this 1 to ADP line, this is called as grand sensible heat factor line. Next calculation is of effective room sensible heat factor. So ERSHF, for that calculation we use this formula, that is RSH plus OASH into bypass factor of cooling coil, and RSH plus OASH into bypass factor of cooling coil, and RLH plus OALH into bypass factor of cooling coil. So for this purpose we have to calculate bypass factor of the cooling coil. So bypass factor for the cooling coil is this line 1 to ADP. So bypass factor cooling coil formula, opposite difference by total difference by TD2 minus ADP divided by TD1 minus ADP. Already we have received value of TD2 from the psychrometric chart and TD1 also from psychrometric chart. ADP is given 5. By putting the values we find bypass factor for the cooling coil. This bypass factor we use in the further calculation. Once again we go to that slide. So by putting here bypass factor value in the formula, we find the calculation and finally we get the ERSHF value, that is 0.6457. Now this ERSHF value we have to locate on the psychrometric chart. So here now on a psychrometric chart scale on this here at 0.64, that was a ERSHF value. So this point we locate here, we say this point has a point D. Then we join alignment circle and this D point. So this line get reference line. To this line we draw a parallel line. Now here this is a I indoor point and this is a ADP. You join these both points. So this line I to ADP, this line, violet color line, and this AD line should be parallel, should come parallel. So that is why here now I ADP line is called as effective room sensible heat factor line. Now the last point is what capacity of cooling coil. So cooling coil capacity means this is a process across the cooling coil, that is a point 1 and 2. So formula will be what? M dot D, that is a total air passing over cooling coil, dehumidified air, multiplied by enthalpy difference between point 1 and 2. H1 and H2 enthalpy we have received from the chart. Dehumidified air quantity we have received from the calculation. By putting all the values we get the capacity in kilowatt. If we divide this by 3.517, then we find the value in TR. So capacity of cooling coil in a TR we obtain. So in this way, in this numerical, we have find all the parameters which are asked, that is what? Room total heat, grand total heat, then condition of air entering to the coil and leaving the coil, that is a TD1, TD2 points. After that we find the different factors, that is room sensibility factor, grand sensibility factor and effective room sensibility factor. And lastly we calculated the cooling capacity of coil in a TR. So this was the total procedure for the numerical. which is based on the case that is a mixing before cooling coil. Let us meet in the next video session. Thank you.